Okay, I made the map. Yeah, so far we discussed this map in chapter 6. Let me add one more. It will be the last topic, which will be this one. Normal approximation to the binomial model. It means we are going to have a binomial model. The binomial. What we had for the binomial? NNP. It's actually we have a binomial model, the binomial distribution. Let me remind you. In the binomial, we had only two outcomes, success or failures, alive or die, male or female, right? To remember what was the N? N was independent number of trials. Please remind the toss a coin 10 times, head or tail, 10 independent trials. P was the probability of success, the probability of head, right? So now we have a binomial distribution. So let me go back to the example. Please look at this example. 6.17. Do you remember this example? 80% chance is to be alive at 65. So we made tree diagram and we applied the binomial distribution. But before N independent trials, only 3. We selected only 3 people. But now, how many? 500 people. So now I can say we have a binomial model, binomial distribution, n equal to 500. But still, probability of success, 0.8. So we have this kind of binomial distribution, n equal 500. Probability of success is 80%. Okay, what is the question? We need the probability exactly 390. Who will be alive at 65? That means we need the probability x equal to 390. Can you remember the probability function? What was the probability function? Which was nx times p to the x times 1 minus p n minus x. You remember? The first one, how many combinations? Success and failures. Do you remember that? So let me plug into the formula to take the probability. N was 500. Now x is 390. We are going to use the function of c to get the number of combinations later. And probability was as 0.8. Power x 390. 1 minus 0.8. 500 minus 390. Okay. Please give me the 500C and 390, please. 500, you can take the C function and plug 390 and enter. Anybody?
I think it was an overflow.
Yeah, it didn't show up overflow.
Is it overflow?
Yeah.
We can't. How can we do? We can't. Your calculator doesn't give us the answer. How many combinations? 500, C, 390. Are you going to give up? Please don't give up. We are going to use the normal approximation. Just a second. Let me go back to the map again. Here is the binomial distribution. And here is the normal distribution and the standard normal distribution. Right? Now, we need a probability. Where? Based on a binomial distribution. How many n? 500. How much was the probability? 0.8. But impossible. In this case, approximately, we can take the probability from the normal distribution. Approximately. Do you know why? Because the binomial distribution looks like bell-shaped. So approximately, we can take the normal distribution from the, what did I say? I'm sorry. We can take the probability from the normal distribution, not the binomial. But look at this. For the normal distribution, what we needed? Actually, not n, not p. For the normal distribution, we needed the mean and the standard normal distribution, right? We can take them from the binomial. How? To remember how can we get the mean in the binomial? N times p, thank you. How about the standard deviation? Square root of n times p times 1 minus p. We are going to use them. For whom? Normal distribution. Okay? So let me go back. So now we had a binomial, n was 500, and probability is 0.8. We need a mean. How? N times p. 500 times 0.8. How much will be 500 times 0.8? What? 400? What does it mean? We selected 500 people. How many people do you expect they will be alive at 65? 400 people. We can expect 400 people out of 500. They will be alive at 65 because 80% of 500 people will be alive. 80% was the chance, right? And also, we need the standard deviation, which will be 500 times 0.8 times 0.2. Can you understand where can I get 0.2? 1 minus 0.8. 1 minus the p. 0.8 will be 0.2. So how much will be the standard deviation, please? 8.94. So now we have a mean and standard deviation. For whom? The normal distribution. So now we have a normal distribution, mean equal 400, standard deviation 8.94. Remember, approximately. What do we need? We need a probability. So let me make a normal distribution, 400, and the standard deviation was 8.94. We need a probability at 380. 380 is lower than the mean 400 here. 380. To remember the map, when we take a normal distribution, then what do we need? A z-score. And then we took the probability from the z-table. Right? So now we need a z-score. At 380. I added just a new topic from the binomial. But now we went to normal distribution with the mean, the standard deviation. It's the same thing. We are going to take the z-score and we are going to take the probabilities from the z-table. That will be the answer. But now, technically, we have to add and subtract 0.5. 380 minus 0.5. And this one will be 380 plus 0.5. Technically, plus and minus 0.5. I will explain to you later why we have to do that.
Where are you getting 380 from?
It was the question.
Oh, okay.
You know, the question was, I'm sorry, you are right, 390, I'm sorry. Yeah.
I was just.
Yeah, I made you confused, I'm sorry. So, it must be 390, not 80, thank you. 390 is 90 and 90. So the 390 minus 0.5 will be 389.5. And this one will be 390.5. So now we are going to take two z-scores at 389.5 and 390.5 from the adjusted scores. So the z-score will be 389.5 minus the mean divided by the standard deviation, 8.94. And the other one will be 390.5 minus 400 divided by the standard deviation, 8.94. So how much will be the z-score at 389.5, please? Negative 1.17. Yes, we need only two decimal places. And how much will be another z-score at 390.5?
Negative 1.06.
Negative 1.06. So now we have two z-scores, negative 1.17 and negative 1.06. What do we need? We need the probability between these two scores. Approximately, it will be the probability at 390. I'm sorry. The probability at 390. But we adjusted a little bit. It's a plus and minus 0.5. So we took the two z-scores, negative 1.17, and negative 1.06. Now what do I need? We need a probability. We need a probability from the z-table. So let me go to the z-table, negative z-table, and I need a probability at negative 1.17. Negative 1.17. Where is the z-table? Yes, here. Negative 1.17. 1.1 and 7. Can you see the probability 0.12, 10? Please keep the probability 0.12 and 10. Let me take it. 0.12. Okay, here. So I mean this one. 0.12, 10. Let me take the other one at negative 1.0 and 6. Negative 1.0 and 6. 1.0 and 6. There is a probability 0.1446. Can you see the probability? 0.1446. What did I say? 0.1446? What do I need? I need the probability between these two z-scores here. How can I do? Take subtraction. How? Bigger one minus the smaller one. So the probability at 390 approximately 0.1446 minus 0.1210. It will be 0.0236. Yeah, it is a long calculation. At the beginning, we had a binomial distribution, but sometimes it is impossible to get the probability. So approximately, we take the normal distribution with the mean and the standard deviation. But remember, we have to adjust a little bit.
Do you always have to subtract and add?
Yes, always we have to do plus and minus 0.5. I will explain to you later. Yeah, just a second.
Is it just on this one or all of them?
Say again?
It's like on yesterday's too on z-squares, or is it just this binomial distribution?
Only this case. Only for the normal approximation to the binomial. Okay, let me explain to you why. We should take the probability from the binomial distribution, but it was impossible. So we used the normal distribution instead of the binomial distribution, right? But we had the binomial in chapter 5. Do you remember the title, chapter 5? Discrete random variable. Countable. Binomial distribution and the Poisson distribution were discrete, countable. random variables. Add 0, add 1, add 2, add 390. Okay? So let me make the clean one. You know, basically, in the binomial model, who is the previous value? Binomial distribution was the discrete type. So the previous one should be 389. And the next one must be 391. Binomial distribution is a discrete type. So we can take a probability at 389, at 390, at 391. It's not between these two. No, not here. Only here, only here, only there. Because, again, the normal distribution was discrete, countable, random variable. But it is not easy to take the probability from the discrete random variable binomial distribution. So instead of the binomial distribution, we tried to take the probability from the normal distribution. Is normal distribution discrete? No. Normal distribution is continuous. So it's actually we need the probability at 390, but we are going to take the probability based on a continuous random variable. So that is the reason why we minus 0.5 to take 389.5 and add 0.5 to take 390.5. How do you think? Who is this for? Who is this one for? I mean, between, in this case, it should be add 0.5 and minus 0.5 will be 388.5. I mean this one. This one will be for 389. We took the probability at 390. How? In this area. Because we have to take the probability from the continuous normal distribution. And the next one, from here to here, this one must be for 391. The reason why we have to do plus and minus 0.5, the adjustment, because binomial distribution was discrete. But the normal distribution is continuous. So because of that, we need some area for the normal distribution from the binomial. So only in the topic, normal approximation to the binomial, we have to do plus and minus 0.5. And then take the two z-scores, take two probabilities from the z-table, and subtraction. Finally, the probability, the answer, is the approximated probability. For whom? Actually, for the binomial distribution. Is it good? So, please try trying to understand what is the normal approximation to the binomial distribution, why we have to do plus and minus 0.5 to take the probability from the normal distribution. And remember, it is approximation.